So if this is IBDP and we are doing equilibrium chapter, and Kc is what? Kc is equal to product to the power of stoichiometry, right? And we're sending this recording to you also, right? Reacting to the power of stoichiometry, right? So if you need afterwards also, right? So that you can use it, right? You don't have to log in for the session. So now going to this thing, now if you see Kc will be what? Kc will be a ratio between product to the power of stoichiometry by reactant to the power of stoichiometry, right? Now going to this thing now what does it mean actually? It means that if you're seeing that the Kc value, if it is greater than 1, right, much greater than 1, so the product concentration will be higher, right? Isn't it? Product concentration will be higher. So we can tell that if the Kc value is much greater than 1, the equilibrium lies almost to the products, right? Is it clear? Right? The equilibrium lies almost to the products, right? Is it clear to you? Fine. Now, if you're seeing that, if you're having that the Kc value, right? Kc value is much less than 1, right? What does it mean? It means that the reactant concentration is what? The reactant concentration is lower, right? Isn't it? Isn't it? Sorry, higher. My God, right? Is it clear to you? Is it clear? Simple. We have to apply maths. If the Kc concentration, if the Kc value is much less than 1, so this numerator will be what? Numerator will be much higher, right? Isn't it? If the reactant concentration is higher, so the equilibrium lies to the left, or the equilibrium hardly has proceeded, right? The reaction has hardly proceeded. Did you get this thing? So the value of the Kc will be telling you that where exactly is the equilibrium lying, right? Now go to the next part, right? Now if you see that when we are studying our equilibrium, right? How do you study? Can you tell me how do you study? We can study the equilibrium by what? By measuring the concentration till it becomes constant, right? Isn't it? Can you remember? 100, 10, 100, 0, then 90, 10, 80, 20, 70, 30, 70, 30, 70, 30. See, it will be remaining constant. Can you see this, right? Right. We have to measure this, right? Till the time the concentration remains constant. Now, Sana, remember one thing, that the equilibrium can reach within minutes. The equilibrium can reach within days, months, and years also, right? Isn't it? So how long shall we wait? Isn't it? How long shall we wait, right? For the equilibrium to reach, right? Is it clear? How long should we wait, right? Isn't it? How long shall we wait? Isn't it? Did you understand this thing? How long shall we wait? Can we have any other parameter by which we can measure the equilibrium? Isn't it? Has achieved or not? Did you get this thing? The equilibrium can reach within minutes, within hours, within days. How long shall we measure? So usually we can find out the equilibrium has achieved or not by measuring the concentrations, right? Isn't it this, right? That till the time the concentration becomes constant. Is it clear? Till the time the concentrations become constant, right? Right? This. Till the time the concentration becomes constant. Did you get this thing? Fine. Did you get this thing? So this is very important that whenever we are seeing a particular equilibrium, we can see that equilibrium has achieved or not by measuring the concentration till the time they become constant, right? Is it clear? Now going to this thing, next thing is that if we see that any equation which is given, right? Any equation which is given, right? All equilibrium, all reactions, right? All reversible reactions have got a literature value of the equilibrium constant, right? At a particular temperature. Did you guys think? All reactions have got a equilibrium constant at a particular temperature, right? Isn't it? Fine. Suppose Kc is 49.5, right? This is a literature value, right? What we do, suppose we are going to the lab and measuring the concentration, not equilibrium concentration, right? We don't know that whether this reaction has achieved equilibrium or not, right? We are studying this reaction, right? We have got a literature value at a particular temperature. We take the same temperature and do this reaction to find out that is the reaction achieved equilibrium. Suppose we went to the lab around 7 a.m. and measured this, right? The concentration, right? They might not be equilibrium concentration, right? We measure the concentration at 7 a.m., right? At around 4 p.m. we go to the lab and measure the concentration, right? What we do, we don't know that whether or not it has achieved equilibrium or not. We don't know. But we can know that how far is that from the equilibrium by what? By putting into a parameter called as equilibrium quotient, right? Is it clear? Putting into a parameter called as equilibrium quotient, right? Now the equilibrium quotient is what? The equilibrium quotient will be equal to what? Will be the same expression, that of equilibrium constant. See, is it clear? Same expression, right? Did you get this thing? Same expression, right? Now, product to the power of stoichiometry by reacting to the power of stoichiometry. Now we put the values at 7 a.m. which you got, right? The concentration, not equilibrium concentration. It can be, it cannot be. We put this, right? See, hi to the power of 2 divided by hi and I. We are getting a equilibrium quotient of what? Reaction quotient of 4, right? Now at around 4 p.m. we went to the lab and measured the concentration. We put it into the same formula, right? We're getting 103. Now this is called as a reaction quotient. Now the equilibrium constant literature value is how much? 49.5, isn't it? Right? 49.5, right? Isn't it? 49.5. Now at around 7 a.m. how much is the reaction quotient we got? 4, right? It's 4. 4 is here, right? We can tell what? We can tell that the reversible reaction has not achieved equilibrium, right? At 7 a.m. It is moving towards the right to achieve the equilibrium. Is it clear?
Yeah.
Now at around 4 p.m. we have got what? Q value of what? 103. So 103 is here, right? So we can tell that the reaction has not achieved equilibrium at 4 p.m. It was moving to the left to achieve the equilibrium. Is it clear? So always draw this diagram. It will be very easy for you to do, right? Is it clear? Draw this diagram. We can easily. It's very easy for us, right? Is it clear? Fine.
Yeah.
Did you get this thing clearly? Fine. So this is the way we find out the reaction quotient, and reaction quotient will be telling us if the Q is equal to Kc, we can tell that the reversible reaction has achieved equilibrium, right? Do you guys see? Now can you quickly do this question? Can you quickly do this question? Wait. This one, huh? Question number 8, right? I'm just coming back quickly. Right?
It gives us.
Use a calculator. Don't really do anything mental, man. Right?
100, which is?
Now, Kc is how much? Kc is 0.9, right? Now write down the chart. Write down the chart like this. Kc is 0.09, right? And Q is how much? Q is 100, right? So which direction this is the Kc? So the equilibrium is, so the reaction is moving towards the left, means towards the reactant to achieve the equilibrium, right?
Yeah.
Isn't it easy? So you have to put what? We have to find out the Q value, and after that we have to find out the Kc value, right? Sorry, we compare with the Kc value, right? The literature Kc value, isn't it? Now see, now Sana. Now if you see that whenever we are seeing any reaction, right? Suppose we are seeing this equilibrium reaction, right? This equilibrium reaction. If you see that whenever we are seeing this equilibrium reaction, right? Isn't it? This. Suppose AA plus BB gives you CC plus DT, right? Now the Kc value will what? The Kc value will be equal to this, right? Isn't it? The Kc value will be equal to this, right? C to the power of C, D to the power of D, A to the power of A, B to the power of B. Is it clear? Fine. Clear?
Yeah.
We are having this reaction. This reaction has got a Kc value of this, right? Isn't it? Clear? Right. Has got a reaction Kc value of this. Now going to this thing, now we have to understand that whenever we are seeing that there's a same reaction, just inverse, right? See, is it clear? Fine. This reaction you're studying, you're getting the Kc value, right? Isn't it? Kc is Kc value. Now, if you're seeing that there's a similar reaction, which is just the opposite to this reaction, right, Sana? Let's see, opposite to this reaction, isn't it? This is just opposite to this reaction, isn't it? Did you get this thing? This is opposite to it. So you don't have to calculate the Kc of this, right? The Kc of this will be what? The Kc will be 1 by Kc. Is it clear? If you are finding out the Kc value of this, now if you are having an opposite reaction like this, what is the Kc value of this? 1 by Kc. Is it clear? You guys think? Any questions? This is a reaction we are studying, and we know the Kc value. We calculate it. You don't have to calculate this reaction's Kc value, just the inverse reaction, right? This Kc this Kc of this reaction will be what? 1 by Kc, right? Clear? Now, if you have got a reaction like this, right? If you have got a reaction like this, right? Now, after this, we are doing what? After this, we are trying to see that there's another reaction which is just multiple of this reaction, right? See, the multiple of this reaction. 2AA plus 2BB gives you 2C plus 2DD, right? We know that we had got a reaction like this, right? Whose Kc value we knew, right? We did, right? Which Kc value we knew, right? Now, if you're having another reaction which is just the multiple of this, can you see this? You don't have to calculate the Kc value of this, right? The new Kc of this will be what? Kc to the power of 2. Is it clear? See, 2. Is it clear? Did you get this thing? I'll be giving you questions right away. Did you get this thing? Get this thing? Fine. Now, if you have got a reaction which is just half, right? Which is just a half of the earlier reaction, right? Half of the earliest reaction, right? Just a half of the earlier reaction, right? Half of the earlier reaction, right? You guys see? Half of the earlier reaction. So that you don't have to find out the Kc. The new Kc will what? The new Kc will be Kc to the power of half. Fine? Means square root of Kc. We have to do square root of Kc. Is it clear? Sana, did you get this thing?
Clear.
Now, if you see this reaction, how to do this reaction? You had got a question I saw, right, in the last session.
Yeah. So this is our Kc, and the.
Now, what is the relation between this reaction and this reaction, Sana? This reaction and this reaction.
Okay. Well, one it flipped.
Flipped. So if you flip the sign, what will the new Kc?
Maybe Kc.
1 by Kc, right?
Yeah.
1 by Kc. Now after that, what is happening? The stoichiometry is, tell me, halved, isn't it? So it will be square root of the square root, isn't it clear? Did you guys see?
Oh, okay, I see.
Fine. Now wait.
So whenever it's halved, you square root the thing.
Yeah, square root. If it is double, you have to see. If it is double, the new Kc will be what? Kc to the power of 2. If it is tripled, the new Kc will be Kc to the power of 3. Is it clear? Fine. Okay, I'm giving a question quickly. Tell me this.
Okay.
Wait. Do this.
Okay.
This question.
So here is our Kc value. This is times by 2. So it'd be Kc squared. Right? It would be Kc squared, right?
Yes.
Okay.
Yes. Perfect.
This
it will be 278 to the power of 2.
Be 1 over Kc because they're flipped. Okay, and for this one, it got flipped. So be 1 over Kc squared.
Wait. Yeah, square root, right? Half. First say that this is half, right? Halved. This reaction is half, right?
Right.
Flipped and half, right? Isn't it clear?
Flipped in half. Okay. I see.
That's all. Yeah. Okay. Now is it clear to you? Now can you open the question paper? Question paper, you had got a question like this.
Okay.
Right? Open the question paper.